Today we're going to be talking about how to find maximum curvature of the function. And in this particular problem, we've been asked to find the point where the function has maximum curvature. Our function is y equals e to the x. Now, usually when we're talking about curvature, it's in relation to vector functions. And we're looking at k of t, where k is the curvature kappa. But in this particular problem, we just have a regular old function, not a vector function, but just a function y in terms of x. And when we're given a regular function y in terms of x, we can use this formula instead of k of t. We're using k of x. This is going to allow us to find curvature of a function in this form. So first, let's go ahead and call this function, instead of y equals e to the x, let's call it f of x equals e to the x. That way it'll match our formula. But as you can see in our formula, we're going to take the first derivative of f of x to get f prime of x. We're going to square that, add 1 to it, and then take that whole value and raise it to the 3/2 power. In our numerator, we're going to need to find the second derivative, and then we're going to take absolute value of the second derivative, and that'll be our numerator. So we're really just working from the inside out. We need to find each of these components and then plug them into our formula. So taking the first derivative of f of x to get f prime of x, of course the derivative of e to the x is just e to the x, so that's going to be our first derivative. Our second derivative of x will be the same. We'll get e to the x because the derivative is still e to the x. And taking the absolute value of our second derivative, of course, still just gives us e to the x because there's no negative involved here. If you know what the graph of e to the x looks like, it's all positive above the x-axis. So taking absolute value doesn't change that at all. We still just have e to the x. So now we have these components, we can go ahead and plug them into our curvature kappa function. So we'll get k of x is going to be equal to, here we have the absolute value of our second derivative, e to the x. So we put e to the x in our numerator. In the denominator, we're going to have quantity 1 plus, here we have the derivative f prime of x, so we're going to get f prime of x, which is e to the x, so e to the x, but then we're going to square that. Then we're going to raise this whole thing to the 3/2 power. So when we simplify here, we need to simplify our denominator. E to the x and then squared is just going to give us e to the 2x. So we'll have e to the x over quantity 1 plus e to the 2x raised to the 3/2. Now we can't really simplify any further, so we'll go ahead and leave this as our curvature function. Now when it comes to maximizing this function, we're going to follow the same kind of process that we use when it comes to maximizing a regular function instead of a curvature function. Remember all the way back to when we first learned derivatives and optimization, we would just take our function, we'd find its derivative, set that derivative equal to 0 to find critical points, and then test those critical points to find maxima of the function. Well, we're going to do the same thing here. We've got a function for curvature, we're looking to maximize curvature, and so all we need to do is take the derivative of our curvature function, set it equal to 0, and find any critical points where this function might have a maxima. So here's how we're going to do that. We're going to take the derivative. In order to take the derivative, we're going to need quotient rule. So I won't write quotient rule out, but we'll go through it here. We're going to say the derivative of curvature function is going to be, now remember for quotient rule, we take the derivative of the numerator first, the derivative of e to the x is still just e to the x, and we multiply that by the denominator without touching the denominator at all. So we say the denominator. Then we subtract, we leave the numerator as is this time, so we leave the numerator as is, and we take the derivative of the denominator. Taking the derivative of the denominator is going to require us to use chain rule. So to use chain rule, we'll bring this 3/2 out in front. This is like power rule here. We bring the 3/2 out in front like this, leaving the inside function completely alone, so 1 plus e to the 2x, and subtract 1 from our exponent. 3/2 minus 1 is 1/2, so we get 1/2 there. But then we just took the derivative of the outside function. We left this inside function, 1 plus e to the 2x, alone, but now we need to multiply by the derivative of the inside function. Well, the derivative of 1 is 0, the derivative of e to the 2x is 2e to the 2x, so we need to multiply by 2e to the 2x. Now, going back to our quotient rule formula, remember we take the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator, and then we divide this whole thing by the denominator squared. So when we square this whole denominator, and let's do it in a different color so we don't get confused later, but basically when we square that whole denominator, this 2 right here is going to cancel with this 2 right here, and we're just left with 1 plus e to the 2x cubed. So in our denominator, we get 1 plus e to the 2x cubed, like this. Now we need to simplify this derivative as much as possible before we set it equal to 0. So we're going to say k prime of x is going to be equal to, the first thing we want to do is cancel out the 2's over here. We have a 2 in the denominator and a 2 in the numerator of this whole term. So those are going to cancel out. We're going to bring the 3 out in front here. We have e to the x times e to the 2x. When we multiply terms with like bases, we add the exponents together, so we get x plus 2x, or 3x. So we're going to have e to the x times 1 plus e to the 2x, all raised to the 3 halves, minus, bringing the 3 out in front, combining the e to the x and the e to the 2x, we get e to the 3x multiplied by 1 plus e to the 2x raised to the 1/2 power. And we have this whole thing here divided by quantity 1 plus e to the 2x all cubed. Now let's go ahead and do some canceling here. So as you can see, we have this quantity 1 plus e to the 2x in each of our terms, just raised to different exponents. So here we have to the 1/2, to the 3 halves, and cubed. So we're going to cancel out 1/2 from each term. So this one's going to go away completely and become 1. When we cancel out a 1/2 from here, we're just going to be left with 1, because it's like 3 halves minus 1/2 gives us 1. So this is going to go away and just become 1. And in our denominator, this is going to go away and become 5 halves. Because we take 3 minus 1/2 gives us 2.5, or 5 halves. So there we go. So now what we can do is factor out an e to the x in the numerator. So we'll say k prime of x is going to be e to the x multiplied by 1 plus e to the 2x, so 1 plus e to the 2x, and then we subtract 3 e to the 2x, so e to the 2x like this, and in our denominator we're just left with 1 plus e to the 2x raised to the 5 halves power. Now we can do a little bit more simplification inside these brackets in the numerator. We get k prime of x is equal to e to the x. Here we have e to the 2x minus 3e to the 2x, or negative 2e to the 2x. So 1 minus 2e to the 2x like this, all divided by quantity 1 plus e to the 2x raised to the 5 halves. Now we've simplified as much as possible, so what we want to do is go ahead and set this equal to 0. We're going to set this equal to 0, and we want to find the points where this function is equal to 0, because that's going to give us the critical points of our curvature function. So setting this equal to 0 means we're looking for the numerator to equal 0, because if the numerator equals 0, then we get 0 over something, which is going to give us, of course, 0. If we set the denominator to equal to 0, it means the function's undefined, so we're really looking at points where the numerator is equal to 0. Well, the numerator is equal to 0 if either e to the x equals 0 or 1 minus 2e to the 2x is equal to 0, because these are multiplied together. Well, we know that e to the x is never equal to 0, so we don't have to consider that one. Really, then that means we're just looking at points where 1 minus 2e to the 2x is equal to 0. So we can go ahead and solve this now for x. We'll add 2e to the 2x to both sides and get 1 equals 2e to the 2x. Divide both sides by 2, e to the 2x equals 1/2. Take the natural log of both sides, so natural log of both sides like this, and that means the natural log and the e on the left-hand side will cancel. We'll get 2x is equal to natural log of 1/2, and then divide both sides by 2, we get x equals 1/2 ln of 1/2. Now, one thing we can do to simplify this critical point further is we have 1/2 inside of our natural log function. Well, 1 over 2 is the same as 2 to the negative 1. So x is equal to 1/2 natural log of 2 to the negative 1 power. like this, because we could move this 2 back to the denominator and this -1 would become a +1 and we'd have 1 over 2 to the first, or just 1/2. So that's how we brought it into the numerator, by reversing that process. So 2 to the -1. But when you have something like this inside of a natural log, you can bring the exponent here out in front and multiply it by the coefficient. So we take this -1, multiply it by the 1/2 in front, and we get x is equal to -1/2 natural log of 2. And this is just all about knowing your laws of logarithms, but this is our critical point, -1/2 ln of 2. Now, because we only found one critical point, because we only have this one critical point right here, we know that that's where the maximum curvature exists. If we want to prove that to ourselves, we can plug this value into the second derivative of k. So what we would do is we would take our curvature function, we already have the first derivative, we'd find the second derivative, again using quotient rule, we'd need product rule as well, and then we could plug this value into the second derivative, show that the result was negative, and therefore prove that this critical point gives us back a maximum. So that's how you would prove it to yourself if you want to. But we know that this point represents the maxima, so what we're going to do is plug this value back into our original function to find the corresponding y value of the coordinate point, so we can give a coordinate point where the function has maximum curvature. So we'll say y is equal to e raised to the x, well, we found x to be -1/2 natural log of 2. So we plug that in, and now we want to find a value for y. Well, the way we're going to do it, we talked about laws of logarithms earlier. We can take this coefficient, the -1/2, and make it an exponent on the 2. So we can say y is equal to e to the natural log of 2 raised to the -1/2 power, like that. When we do that, we can see that we have e raised to the natural log of something. We'll get e and natural log to cancel with one another, and we just have y equals 2 to the -1/2 power. Now, to make that exponent positive, we'll move this 2 to the denominator. We'll get y is equal to 1 over 2 to the 1/2 power. See how that exponent becomes positive? Well, of course, raised to the 1/2 power just means the square root, so we get y is equal to 1 over root 2. Now we know that the coordinate point at which maximum curvature exists for this function is the coordinate point -1/2 natural log of 2, comma, 1 over root 2. So that becomes our final answer, and if we wanted to find maximum curvature itself, like what is the actual curvature at this point where the maximum curvature exists, we could just take this value for x and plug it into our curvature function. So we found the curvature function right here without the extra exponent here, the 2, but this was our curvature function. So if we just take this x value and plug it in, then we can find curvature at this point. But this is the coordinate point where maximum curvature occurs.